To summarize, what we care about in these two chapters is the energy principle. So our energy model here says that we can have an environment and a system, and that within the system, energy is transformed, and we have three types of energy that we worry about. We also have energy transferred in and out of the system by work. So our final best versions of conservation of energy are given by these two equations. So getting to this point, we have to understand what all of these pieces mean, but this is really the point that we're trying to get to, and it takes, unfortunately, two chapters to get there. So a new idea in these chapters that's very important are the idea of springs. So if we want to define a spring force, the ideal spring is governed by this equation where you have the spring force is negative times the spring constant K times the displacement from equilibrium. So there's some equilibrium length of the spring where it wants to sit if there are no forces exerted on it. And then we think about our object moving on the spring, it's not always going to be at that position. So keep in mind that negative sign tells you that if you're displaced to the right, if the spring is stretched away to the right from equilibrium, which you should always show on a sketch, that your force is then to the left. So that's where your minus sign is. Be very careful about signs. This is, of course, for an ideal spring, and in the real world, nothing is truly ideal. There are many things we are going to model as ideal springs, and that can include, for instance, rubber bands, elastic bands, things like that. And so even though those aren't springs per se, we will still use this model. So be careful about it. We've introduced the idea of potential energy being an energy that is stored in the state of our system. So typically that means the position of our objects within the system. Now this is where it's very important to define your system and your environment carefully, since if you define, for instance, gravity to be coming from external to your system, then that would actually be work. But if you consider the Earth to be part of your system, now you can define gravitational potential energy. So this only works for conservative forces. There are certain forces that you cannot define potential energy for, and it's actually related to work, though we don't worry about this too much. Just try to use potential energy whenever possible. This is related to force, such that the derivative of your potential energy, but with a minus sign, will give you the force that has led to it, and vice versa. You can integrate force and to get potential energy, but with a minus sign. Now, one thing that the book tries to be careful about is that potential energy is really about the system, not just a specific object, but many of us, when we are talking about it, we tend to be a little sloppy and say the potential energy of the ball. The ball itself does not have potential energy. It's the Earth ball system that has potential energy. So two types of potential energy that we have defined are gravitational potential energy, which depends on the mass of the object, g of whatever planet you're on, for us that's Earth, and then the height you are above the Earth. It doesn't depend on the speed, it doesn't depend on the x position. It doesn't depend on how you actually even got to that height. We talked about the idea that when you go to do an equation, what matters is the change in potential energy, such that you have to set your y equals 0 value to be somewhere, but your work will still be okay if you choose a different y equals 0 position. So make sure you define y equals 0, but there isn't necessarily one correct choice over another. Elastic potential energy is going to be for springs, and again, anything that we model as an ideal spring. And delta S is your displacement from equilibrium, and that's going to be squared. So this potential energy curve looks like a parabola. So K in this case is your spring constant. The potential energy doesn't actually depend on the mass of the object attached to the spring. Energy diagrams were one way that we actually visually represent situations with energy. However, you typically don't draw these yourself, but you're asked to interpret them. So you are welcome to draw them if you think you have a situation where it would be good to do so, but many real-world situations, it's pretty challenging to start by drawing this. There are two lines to worry about: the potential energy curve, shown here in blue, and the total energy line, which must be horizontal. You only can really do potential energy diagrams for isolated systems that do not have a change in thermal energy. So mechanical energy is conserved, and that's the only thing we're looking at. The horizontal axis is position. And we then can say for a given position that our object is at, we can get its potential energy at that point, and we subtract the potential energy from the total energy line to get the kinetic energy at that point. Keep in mind that the total energy curve is dictated by the initial conditions of your object. Where did it start and how much kinetic energy did it have at that point? So for instance, if it starts at a point here, but actually has kinetic energy, we would add on that K initial, and we would say that our initial energy line is actually up there. So be careful about that. Turning points are wherever your total energy line crosses the potential energy line. At that point, the particle stops, has zero kinetic energy, and turns around. Maxima and minima in the potential energy curve can be used to identify stable and unstable equilibrium, and you can also look at the slope to understand how the forces are acting. Two important definitions that I haven't otherwise presented yet is the change in thermal energy of our system. We never break it into initial and final, it's just a change, is going to be the kinetic friction force times the length that the object has traveled. And the book frequently calls that delta S, but this is true even if it's a curved path, which is why I use curly L. So the length it's traveled and the frictional force tells you the thermal energy that has been transformed from mechanical energy. Work from a single constant force is given by the dot product between the force and the displacement, and we've talked about the definition of dot products so that you can say FR cos theta. Note that this is only for a constant force, that if what you actually want is a force that is varying with time or position, you actually have to do the integral then. So be careful about that. This is only for a constant force, but that's normally the simplification we can make. Finally, there are two notes that I want to make in regards to the problem-solving rubric. There are three new representations that have appeared, but the most important one is the first one. This is the before and after sketch. For kinematics work, you were expected to do a sketch where you labeled, for instance, multiple time points. So you have a time initial, a time final, you possibly have times in between. For energy, we never care about time. We only care about before and after. So you should have a position or a configuration of your system that is before and a configuration of your system that's after. And possibly you might have some intermediate points as well, but that's less common here. You might have an energy diagram, but you're normally asked to interpret that rather than draw that. And energy bar charts are an option if those are helpful to you. So finally, we have some new models in this section. They're not in boxes, but they're very important. One is the model of an ideal spring, that we are going to be modeling many different types of objects as ideal springs, and we are then going to use the spring force and spring potential energy equations. I want to note that Hooke's law is not actually a law, it is kind of a model itself, so ideal springs go with Hooke's law, not really a law. Isolated systems are also a modeling choice, that you can define your system however you want, though typically there are better choices than others. And when you say that I have defined my system so that it is isolated, that is an approximation, that no real-world system is completely isolated, but we typically make a choice so that we can consider any interactions with the environment negligible. So please be careful and make sure to start thinking about these two models in your problem-solving work.